So let us consider two queries and a document. We see that for the first query, the result is typically the empty set here, but there is a tuple that is satisfiable, that is an A. And this is because we can insert a B with a child A, and the result of the query changes to the tuple A. If we look at the second query, we see that $y can be matched to any update that is brought by function f. And since we are in an infinite language, we talk about an infinite language, there could be an infinite number of satisfiable tuples. We use a notion that are generalized tuples to represent in a finite way this set of infinite tuples. So actually a generalized tuple consists in variables and in constraints over these variables. We use a relational representation of trees. So root, child, descendant, label, these are the standard relations to which we add function that actually tells if a node is a function call or not. We use non-recursive data log to compute the result of the query over the document. And to compute satisfiable tuples, we use generalized tuples and data log with constraints. Now, the scenario is a pair that consists in a data part, so a tuple, that is a generalized tuple, and a provenance part, that is another tuple that talks about the way each of the node of the query could be matched, could be matched in the could be matched to the query. So here we have a query and we have a document. So the star notations means that the data is already in the document. So we see that A of the query is already in the document, and we represent here with a star. The B of the query is not in the document, so it has to be brought by the only function there is in the document. It is an F. So we put F here. The C is already in the document. We have a star here, and the $x, that is the output, has to be brought by question mark F. So this is one possibility. The other one is that can be matched with the C. Not really important. The scenario is just an example. Now, it turns out that actually not all the scenarios that are here should be considered for our analysis. And that is because some scenarios are more important than others. We have a domination relation that says this. Typically, we consider that a tuple is that a tuple dominates another one if it can result in the same satisfied tuples, but with less updates. Okay, so by the time that the tuples here become satisfied, they have already become satisfied through the first scenario. So the second scenario is completely useless. So we can ignore the dominated scenarios in our analysis. Now, if we consider the whole set of non-dominated scenarios, and if we look at the provenance part for each scenario, well, we can easily see how what are the functions that are relevant, because they are those that appear in the provenance part. Okay, so more, we can even do more. The place in the provenance part tells how these streams are relevant, meaning what kind of subqueries the updates brought by those streams should match. So this is typically what this long I skip this. So now relevance is very important for the optimization, and that is because we can unsubscribe to streams that are not of no interest for a particular view. We can filter to reduce processing in the Abstract engine, and if we are in a distributed setting, This is even more important because we can push filters to the data sources, and thus we reduce communications. We have considered in the implementation of the prototype many extensions like active updates here, streams that terminate by sending an end of stream message that the engine can take advantage of to recompute the satisfiability and to improve its performance. Then we have added time to documents, and we have done this by adding timestamps to the nodes, and the timestamp of a node represents the moment in time when the node has been inserted into the document. The counterpart is that on the queries we have added systems of inequations to compare timestamps between them. There are other interesting extensions that could be added, like management of the if messages, queries with negations, and typing of the document and of the functions. We have implemented an Axlog engine, and there are lots of technologies inside. Typically, the Axlog algorithm maintains the incrementally and filters the inputs, and non-incrementally computes satisfiability and relevance. The architecture consists in several modules. The first one is the compiler that compiles the data log program out of the view query and the active document. Then the tuner computes the satisfiability and Axlog relevance and installs the filters. And then we have the maintainer that maintains the view by evaluating incrementally the program. We have used a generator of documents and queries to do experiments. And there are typically several parameters for it. One of the most important is the pertinence factor here that is used to tune the potential impact of an update to the view. Now, in the first experiment, we have measured the gains that are obtained with our methods when we vary the size of a stream. And we have considered 4 cases. The first case is the baseline. So for each update, we reevaluate completely the view. In the second case here in blue, we have added satisfiability, relevance, and filtering. To the third one, we have also added differential. And to the fourth one, we have added caching. So we typically see that after a reasonable number of updates, we can reach gains of about an order of magnitude in cost. Now, the second experiment measured the performances when the pertinence of the updates for the view is varied. Okay? So we have started with the intuition that when we have low pertinent updates, our methods should be very efficient, and this is because of the filtering mainly. So this is what we see here. Now, our methods are quite efficient, and especially for long streams with low pertinence updates. And the question is, does this scale? We have conducted the experiments that show that the methods scale with the size of the documents and with the number of function calls of streams in the document.